Hello, sir.
Yeah, yeah.
You're audible and visible, sir.
Okay.
Not able to speak through Zoom.
Okay.
Share screen, full screen, and in 1 minute you can begin, sir. when
Okay.
you're ready.
All right. Thank you.
Thank you, sir.
Right. Thank you. Hello, students. Welcome to a session with Time, a live session on this topic, redox reactions, which is part of chemistry. So, before we begin, I want you all to have a live session on this topic. I want you all to have a look on this channel. So for any subject related things, you might visit us. For interesting videos, you might subscribe. You can have your preparations for entrance exams and also board exams done in a good way. So shall we begin? So this particular session is on redox reactions. Now, before we begin, let us check what do we mean by oxidation and reduction. Now, before we actually begin, this particular redox reactions needs to be understood. A redox reaction is one where both oxidation and reduction are taking place. You know that oxidation and reduction cannot happen in an isolated manner. So both oxidation and reduction take place in a single system, which means that if you take a particular reaction, which is a system that we are considering, both oxidation and reduction take place. Let us say that there is a substance A reacting with the substance B. And if we say that A has got oxidized, it means that B has got reduced, which means that B is oxidizing A or A is reducing B. So it is a mutual activity. So a redox reaction is oxidation and reduction taking place in a given reaction. So oxidation and reduction cannot take place in an isolated way. They cannot be isolated. They cannot be separated from each other. Now, with this in mind, let us look at the definitions of oxidation and reduction. Now, the oldest definition of oxidation and reduction we might have read in our childhood. Yes. Now, oxidation, if you're looking at, we'll say is gain of oxidation, oxygen, or loss of hydrogen. Similarly, reduction is gain of hydrogen or loss of oxygen. This is the oldest definition that we have come across, right? For quite some time, we have been using this oxidation and reduction concept in terms of either gain of oxygen or loss of hydrogen for oxidation, or gain of hydrogen or loss of oxygen for reduction. But then when our knowledge advanced, we came to know that oxidation is loss of electrons. So we wrote loss of electrons is oxidation. We know that electron was discovered as late as in 1897. You know that J.J. Thomson discovered the electron. So till then, we had no concept of electrons. So now, because electrons, right? In fact, electrons are the ones that actually take part in the reactions. So oxidation is loss of electrons. So loss of electrons is oxidation, and gain of electrons is reduction. So this is a newer definition of oxidation and reduction. Loss of electrons is oxidation. If you think that this is a lion and this will roar like this. So it is easy to remember. Loss of electrons is oxidation, or gain of electrons is reduction. But then as our knowledge advanced further, we came to know what is an oxidation number. Then we took oxidation as increase in oxidation number, and reduction is reduction of oxidation number. So this is a new concept, right? Oxidation number or oxidation state, right? So there are three definitions, and we are going to take up the second and the third one for balancing redox reactions. Now this particular thing, loss of electrons, gain of electrons, right? That is in a reaction where loss of electrons is happening and gain of electrons is happening, right? The method that we employ is the ion electron method. Ion electron method employs this concept of oxidation and reduction in terms of electrons. This is also called the half reaction method. Ion electron method is also called the half reaction method. By large, this method is the most accurate. Why? That we'll check now. This particular method, that is a third one, where the definition of oxidation and reduction are taken in terms of oxidation number changes. This method, that is oxidation number method, right, is an easier method. Easier means it's a faster method, it's a quicker method. But the problem is, if we are stuck in this finding out of oxidation number, the entire thing will become a mess. So oxidation number method, if you are very, perfect with the oxidation numbers calculation, then this method is the best. If in case we have no knowledge of oxidation number, we do not know what is oxidation number, we can take up this ion electron method comfortably. Though it may take some time, it is accurate. Right? With these things in mind, shall we start spending some time on finding out oxidation number? Now, if we are going to continue this, I hope without papers it is not possible, right? So be ready with the papers. We'll start doing calculation of oxidation numbers. Now, oxidation numbers, how to find out oxidation numbers, that requires certain rules. So we'll first take up the rules. Now, the first rule is oxidation number of any alkali metal or group 1 element, right, is taken as +1. We know what are all the group 1 elements. All are metals: lithium, sodium, potassium, rubidium, cesium, and all those. Then the second one is oxidation number of group 2, which is alkaline earth metals, is always +2, right? We have beryllium, magnesium, calcium, strontium, barium. Now, what are these oxidation numbers of group 1 and group 2 in? They are in their compounds, right? If you take up the compounds of alkali metals and alkaline earth metals, They are always +1 for alkali metal, always +2 for an alkali metal. The third one is oxidation number of fluorine is always -1 in its compounds. Clear? So these are the three things which are always maintained. Now all other elements will have to follow from these. The fourth one we will take up is for oxidation number of hydrogen, which is mostly +1. Most of the cases, except in hydrides, which are metal hydrides. Hydrides made up of or hydrates of metals, it is -1. Then oxidation number of oxygen is mostly -2, but it could also be -1 in the case of a peroxide. It could be -0.5 in the case of a superoxide. It could be -1/3 in the case of an ozonide, or it could depend on the halogen fluorine in its compounds such as OF2 and O2F2 by considering the fluorine's value as -1. Right? We'll see now how to go about getting the oxidation numbers of all other elements. So the fixed ones are 1, 2, and 3 always in their compounds. Right? Next thing is that if you have only one atom or an ion, it could be, let us say, Na, or it could be a Ca2+, or it could be a Cl-, right? The oxidation number is equal to the charge on the atom or on the ion. For an atom, if it is a neutral atom, the charge is 0. For example, Na, the oxidation number is 0 because it is an isolated atom. Similarly, isolated Ca2+ will have 2+ as the oxidation number. Isolated Cl- will have 1- as the oxidation number. Clear? So this atom or ion, if it is isolated, an isolated atom or an isolated ion will have the oxidation number as directly equal to its charge. Clear? Moving on to the 7th point under this, the sum of oxidation numbers of all the atoms in a given species is the charge on the species. For example, suppose it is MnO4-. I take up oxidation number of Mn. I take 4 into oxidation number of oxygen, and that whole thing is equal to -1, which is the overall charge. So sum of the oxidation numbers of all the atoms present in a given species is charged on that entire species. Clear? So with all these things in mind, we'll be able to find out the oxidation numbers of various elements. One simple thing we'll do here to start with OF2, it was. Now oxygen's atomic oxidation number plus 2 into oxidation number of fluorine should be equal to the charge. What is the charge on this? It is 0 because it is neutral. So I'll write here, let us say oxidation number of oxygen as X plus 2 into fluorine is always -1, and that whole thing is equal to 0 because the charge is equal to 0. So X is equal to +2. Come back to this place. Now in OF2, oxygen has got a +2 oxidation state. Similarly for O2F2, if you calculate, you'll get a +1 value. Clear? So like this, we'll be able to come to a conclusion. Now, one word about this peroxo. Peroxo is O single bond O. If you have O of this kind, each O will be -1. That is what is peroxide we talked about. Peroxo means O single bond O. And superoxo is O2 with 1 minus. This is actually O2 with a 2 minus. This is peroxo. This is superoxo or superoxide. Clear? So based on this, if you are clear, if you have noted down, we'll start doing the calculation for various elements. Is this clear? Now the first three are the ones which are always fixed, and all the remaining will depend on them, right? Using this sixth one and the seventh one, right, as a basis, we'll find out for the following now. I hope this is clear. Shall we move on? Now calculating oxidation numbers, this we have already done, is +2. This is +1. This is a metal hydride, so sodium will decide. So I'll put it here. Sodium is +1. If hydrogen is X, and that whole thing is equal to 0 because NaH has got no charge. This is neutral. So X is equal to -1, which is what we wrote. Hydride is, so metal hydride is having hydrogen with a -1 as the oxidation number. Clear? Next, calcium hydride is similar. Calcium is 2+, so calcium will decide. Calcium is group 2 metal. +2 plus 2x equals 0. So X is again -1. Na2O. So Na will decide. So this is Na with +1 and oxygen, and that whole thing is equal to 0. So this is X equals -2. This is normal oxide. This is peroxide. So here you will find oxygen as -1. That you can do and check. Barium, I'll do for you. +2 plus 2x equals 0. So X is equal to -1. -1 means it is peroxo. This is superoxide. So you'll find this as -1/2. This is ozonide. We'll find it as -1/3. This is hydrogen peroxide. Peroxide. So again, -1. I want you to spend time on doing these, right? We have got some, as you will see, how many such examples or how many questions are there based on this. Now nitrogen, this is called nitrous oxide. You can do the calculation. I'll show it for you for the first one. So 2 nitrogens, so 2x. Oxygen, you take it as -2 because normal oxygen it is. So it is 0. So X is equal to +1. So this is nitrous oxide, that is laughing gas, +1. Nitric oxide, +2. This is nitrogen sesquioxide, +3. This is dinitrogen tetroxide, +4. Dinitrogen pentoxide, +5. Right? See how a variety of oxidation states is given by nitrogen. Then NH3, ammonia. I'll do it for you here. So X +3 into +1. Hydrogen is +1 here because hydrogen is not attached to a metal. So X is equal to -3. So this is -3 here. N2H4, hydrazine, which is also used as a rocket fuel and also as a reducing agent in the Wolff-Kishner reduction, isn't it? So this is -2, that you can do it and see. This is hydrozoic acid. This I'm going to do it for you. So hydrogen is +1. 3 nitrogens with X as the oxidation number equals 0 because that is a charge. So X is equal to -1/3. Hydrozoic acid, -1/3. This is sulfur. Sulfur is -2 in this. Here sulfur. So sulfur is X. There are 2 oxygens. Each oxygen -2 equals 0. So X is +4. Clear? So I wanted to do this 11 to 15. 11th we have done already. So 12 to 15, you can do it for yourself and then check whether they are really true. You may take a screenshot if you need. Clear? Now sulfur trioxide, this is +6. This is sulfurous acid, +4. Sulfuric acid, +6. We'll do this 22nd one. How this has come. 2 hydrogens, so 2 into +1. Plus sulfur, which you're going to find out. Plus oxygen is -2, and that whole thing is equal to 0. So X -4 equals 0, so X is +4. Now look at this H2SO5. We need to look at the structure, because in some cases you'll find that the oxygen is not the normal oxygen. Normal oxygen is having a oxidation number of -2, but this is not the normal oxygen here. As you'll see here, HO, S double bond O, double bond O, 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 H. We know that whenever we have this O single bond O, it is peroxo. So this is -1. This is also -1. That hydrogen is +1, no doubt. This oxygen is -2, normal oxygen, normal oxygen, normal oxygen, and then +1. When you do for this sulfur, we'll find that sulfur is +6 again. How that is coming? Let us look at this sulfur. Sulfur is X, let us say. Now these two oxygens are -1, -1. There is a hydrogen +1. There is another oxygen top, double bonded O. At the bottom, double bonded O. Then on the left hand side, -2. Then hydrogen +1 equals 0. So -1 and +1 will go away, right? This -1 and this +1 will go away again. So X -6 equals 0. So X is +6. Now this is nothing but oleum, fuming sulfuric acid. So this you can also do it for yourself. I'll put the structure here. HO, S double bond O, double bond O, O, S double bond O, double bond O, OH. All are normal oxygens. If you want, you can consider this OH as -1 as a unit, -1. There is a -2, there is a -2, there is a -2 here, again a -2, again a -2. So like this, there are two sulfurs here. So 2x we need to take up. How many such -2s are there? 5 such -2s and 2 -1s, and that whole thing is equal to 0, is it? Correct? So X is equal to, X equals 12 by 2, so +6 again. H2S2O8 is having a peroxo linkage. HO, S double bond O, double bond O, O single bond O, single bond O, S double bond O, double bond O, and then OH. Again, this will be +6 that you can do for yourself, taking only these two oxygens as -1. All the remaining oxygens are -2. So 24 is called peroxo monosulfuric acid, and 26 is called peroxo disulfuric acid. Peroxo monosulfuric acid is also called the Carros acid. And H2S2O8, that is peroxo disulfuric acid, is called the Marshall's acid. Then you can do for this one, 27, I'll do it for you here. 4 sulfurs, 4x plus 6 into -2 equals -2. So 4x is equal to 10. So x is equal to 2.5. This is tetrathionate. So x is 2.5. Here, phosphorus, you may find for yourself, is +1. This is +3. This is +5. You can check. The first one is hypophosphorus acid. The second one, that is 29th one, is phosphorus acid. And 30th one is phosphoric acid. Clear? So these things you can check, right? For want of time, I'm not doing this. But wherever the thing looks more difficult, I'll show it for you. MnO4 2- is manganate. 31 is manganate, 32 is permanganate. So manganese, X plus 4 into -2 equals -2. So X is +6. And here you know it is +7. This is chromate +6. Dichromate +6. We look at this CrO5. CrO5 has a structure of this type, which is also called the butterfly structure. So this is now again peroxo. So -1, -1, -1, -1, and then -2. So x plus 4 into -1, -2 equals 0. So x is equal to +6. If we blindly take oxygen as -2, we would end up in a value of plus 10. Plus 10 is not possible because chromium does not have 10 valence electrons to lose. It has got only 6 valence electrons, D5, S1, is it not? So maximum is only 6. Carbon monoxide plus 2. Carbon dioxide plus 4. We'll do this 39th one. 6 carbons, so 6x. 12 hydrogens, 12 into plus 1. Plus 6 oxygen, 6 into minus 2. Whole thing is equal to 0. These two will cancel out. So x is 0. So carbon is in 0 oxidation state in glucose or fructose. And in methane, x plus 4 into plus 1 equals 0. So it is minus 4 here. Clear? I wanted to check 38. Clear? Remaining things I think we have done, except 32, 33 and 34 in this. I hope this is clear. Few more we'll take up. HOF, it's a very interesting example here. Hydrogen is plus 1. Oxygen, you take it as x. Fluorine is always minus 1. Whole thing is equal to 0. So x is 0. Oxygen is in 0 oxidation state. Clear? Whereas here, this is plus 1. Oxygen, you can take it as minus 2. And chlorine, you have to find out, equals 0. So chlorine is in plus 1 oxidation state. We know that fluorine can never be plus 1. So fluorine is always the deciding one. But chlorine will depend on oxygen, because oxygen is in one of the rules there. Chlorine, we have not set any rule for chlorine, is it not? So the 42nd one is called hypochlorous acid. This is chlorous acid plus 3. Chloric acid plus 5. Perchloric acid plus 7. Hypochlorous, chlorous, chloric, perchloric. Then this is hyponitrous acid. This is nitrous acid, nitric acid. This is plus 1, this is plus 3, this is plus 5. You can do it and then check. Then the last one, I'll do it for you, Fe3O4. So 3x plus 4 into minus 2 equals 0. So x is what? X is 8 by 3. Is it not? But then we know that Fe3O4 is a combination of FeO and Fe2O3. Clear? Now, this is ferrous oxide, and that is ferric oxide. Ferrous, you know, is in plus 2 oxidation state. Ferric means plus 3. Now, there are how many ferric? 2 ferric. So 2 into plus 3 plus 6. How many ferrous? Just 1. So plus 2. Add up, it is 8. And how many atoms are sharing it? 1 Fe from here and 2 Fe from there. So by 3. That is how we got x as 8 by 3 is an average value. We've got 2 different environments. One is ferrous, the other is ferric. It's a mixed oxide. I hope with all these things, you are now more familiar with how to find out the oxidation states or oxidation numbers of various elements depending on certain rules, right? We have framed the rules, and then based on the rules, we have come to a conclusion regarding the oxidation number of various elements in their compounds. So some 50 examples we have taken. So 50 questions we have answered here, isn't it? Next, we'll move on to what are disproportionation reactions. Disproportionation reactions are also redox reactions. They're also redox reactions. But then what is a disproportionation? Why it is called disproportionation? Disproportionation seems to be a special name, isn't it? It's a special case of a redox reaction where a single substance undergoes both oxidation and reduction. Let us say that one element here had an oxidation state of 3, right? And it is converted to B, right? With an oxidation number of 1 for that element, particular element. And here it is, let us say 5. So for that particular element in A, the element is common in A, B, and C. I'll show an example. But then before that, let us check what is the disproportionation part here? So 3 is being reduced to 1, but 3 is also getting oxidized to 5. So there is one element which is common in A, B, and C. In A, that element had an oxidation state of, let us say, +3. But then in B, its oxidation state has come down to +1. And in C, it is +5. So it is undergoing both oxidation and reduction. So any substance that undergoes both oxidation and reduction is said to undergo disproportionation. So disproportionation means oxidation and reduction happening on the same species. Clear? On the same atom, it is both oxidation and reduction taking place. So let us consider chlorine turning into chloride and hypochlorite. Now here chlorine has got an oxidation number of 0 because there is an element. See, in any oxidation number, there needs to be two different elements. Suppose A is attached to some B, right? A and B are dissimilar. Then A will have an oxidation number, B will have an oxidation number. But you will not have an oxidation number for A attached to A or O attached to O, right? Or nitrogen attached to nitrogen, right? When the element is the same element is there even in a molecule, then it is 0. For this chlorine, we said atom or ion, whatever is the charge on that, it's -1. This we can calculate. Oxygen is -2, chlorine is X, and that whole thing is equal to -1. So this is +1 now. So what has happened to the 0? The 0 has undergone reduction as well as oxidation. Clear? So this is a disproportionation reaction. This will happen in cold alkali. So chlorine disproportionates in cold alkali to form chloride and hypochlorite. Clear? So like that, we can have a sulfur turning into a sulfide and a thiosulfate. Here it is 0, here it is -2, and here it is +2. So this is reduction and that is oxidation. Clear? So like this, we have got lots of disproportionation reactions. Whatever happened to chlorine will also happen for bromine and iodine, but not for fluorine. Fluorine never undergoes disproportionation because fluorine can never lose electrons. Fluorine can never undergo oxidation. Fluorine will undergo only reduction. It can only gain electrons. It cannot lose electrons. Clear? So these are some of the, one more example we can check here. For example, if we take white phosphorus, it will turn into phosphine and hypophosphite. This is 0 because there is the element. This is -3 because hydrogen is +1, and this is +1. So this is reduction and that is oxidation. Clear? So like this, we have disproportionation reactions taking place. They are a special case of a redox reaction where a single species undergoes both oxidation and reduction. The opposite of disproportionation is comproportionation that you will see now. In a comproportionation reaction, two species, for example, let us say H2S and then SO2, they turn into S. Of course, hydrogen, H2O will form as the byproduct there. So here sulfur is -2. The same sulfur here is +4. But here the sulfur is 0. So H2S is undergoing oxidation while SO2 is undergoing reduction. So we said disproportionation is a single species turning into an oxidized and a reduced species. But here there are two species, different ones, which are forming a common substance. That is comproportionation, which is the opposite of disproportionation. In a comproportionation, you have the same element sulfur, and sulfur here, right? On the left, you have two different species. On the right, you have a single common species. So that is comproportionation. I hope this is clear. So this is also a redox reaction. It's a special case of a redox reaction. Now here -2 is undergoing oxidation to 0, and here +4 is undergoing reduction to 0. Clear? So this is a comproportionation reaction. Now let us balance redox reactions. We said that there are two methods. One is the ion electron method, also called the half reaction method, and the other one is the oxidation number method. We said that this is based on the second definition of oxidation and reduction. Loss of electrons is oxidation, gain of electrons is reduction. And oxidation number method is based on what the oxidation number changes. Either it increases for oxidation or decreases for reduction. So this is oxidation and this is reduction. So oxidation number method requires a knowledge of oxidation number, right? Whereas ion electron method doesn't require any knowledge of oxidation number, right? All that we need to do is balance a reaction by doing an oxidation and reduction in terms of loss of electrons or gain of electrons respectively. Now, shall we move on to the first method, ion electron method? Yes. So in this ion electron method, what we are actually doing is we are splitting the reaction into two halves. Then balance each half separately. Then to the side deficient in oxygen, add H2O. To the side deficient in hydrogen, add H+. H+ you can add only in an acidic medium. If it is in basic medium, what do we have to do? We'll have to add equal number of OH minus ions on either side. This side, left hand side, and also on the right hand side. Then add electrons to balance the charges in each half reaction. See, we had split the reaction into two, one for oxidation, one for reduction, let us say. And each half reaction is to be balanced separately. And while we are balancing, whichever side, whichever half reaction had an oxygen deficient, right, there you add H2O. If one oxygen is deficient, add one H2O. Or if one hydrogen is deficient, add one H+. But then remind yourself, if it is an acidic medium, you need not do anything. But if it is in a basic medium, whatever H+ addition you have done, you have to add OH minus on both the sides in equal numbers. And then up to 4, it is mass balance. 5 is charge balance. Any reaction is balanced mass wise as well as charge. So we'll have to do mass balance as well as charge balance. For charge balance, you're using what? Electrons, right? And then make the number of electrons equal in both the half reactions. And finally, what? Add the two half reactions to eliminate electron. There should not be any electron in the final equation. Clear? So what we have done, we have split the reaction into two halves. You have balanced each half reaction separately. And to the side deficient in oxygen, in each half reaction, add H2O. To the side deficient in H, add H+. If it is an acidic medium, you can simply leave it like that, because H+ can exist in acidic medium, but H+ cannot exist in basic medium. So you'll have to remove that H+. How to remove that H+ by adding OH-, because H+ plus OH- gives rise to H2O. So when you add OH- on any one side, you'll have to add OH- on the other side also, because otherwise it will be thrown out of balance. And then that is up to that mass balance has happened. And then add electrons to balance the charges. Now, before the third came, one more point is there: balance all atoms other than oxygen and hydrogen. First balance atoms other than oxygen and hydrogen. Then start balancing the oxygen, then the hydrogen, and then add electrons, equate the charges, make the number of electrons also equal, and then finally add up the two half reactions to eliminate the electron. That is the end of this method, right? All these will be put to use when we are doing the real question. Clear? Next, in the oxidation number method, all the things are same. The only thing is each half reaction. Let us say, I'll put it here, a real thing here, MnO4 minus plus Fe2 plus turns into Fe3 plus and then Mn2 plus. What we need to do is put the oxidation numbers above the species which are undergoing oxidation and reduction. So here Mn is in +7 oxidation state. Fe, whatever is a charge, that is the oxidation number. Here also +3. Here also +2. So first put these oxidation numbers above the species undergoing oxidation and reduction. You know that MnO4 minus has Mn going from +7 to +2. And then Fe2 plus is going from +2 to +3. Clear? Next thing, what you do, take the change in oxidation number here. So this is 1. The change in oxidation number there is 5. Whatever is the change in oxidation number of one species will become the coefficient of the other species. So MnO4 will be 1. And MnO4's change in oxidation number was how much? 5. That 5 will come to Fe2 plus. This is how the oxidation number method starts with. So first we start with putting the oxidation numbers above the elements. Then look at the change in oxidation numbers. And then change in oxidation number of one will become the coefficient of the other. That is how this 1 has become the coefficient of MnO4 minus and 5 has become the coefficient of Fe2 plus. So we have got the coefficients on the left hand side. Looking at the left hand side, balance the right hand side. So if you have 1 Mn, we need to have only 1 Mn there. If you have 5 Fe, add 5 Fe there. Now this is atoms other than oxygen and hydrogen balanced. Next thing is, look at the oxygens. How many oxygens are there? There are 4 oxygens here. There is no oxygen here. So I'll put simply 4H2O. Because what we said, to the side deficient in oxygen, put H2Os. If there are 4 oxygens deficient, add 4H2O. But then while putting this, we have put 8 hydrogens here. So on the left hand side, there are no hydrogens. So put 8H plus. So hydrogens are also balanced. And if I say that this is an acidic medium, this takes place in an acidic medium, then no need to do anything on this. Now look at this. The charge is automatically balanced. This is 8 plus and 10 plus is 18. 18 minus 1 is 17 plus. On the right hand side, this is a 15 and a 2. So 17 plus again. So quick, is it not? You need not split the reaction. And you need not have all the electrons coming in. You need not equate the electrons. All those things are skipped. So we have bypassed all those things and then got this. But then when is this successful? Only when you know the oxidation numbers, whether the oxidation numbers are true or not, whether the calculation was correct or not, right? So if you know the oxidation numbers, this method is ultimate. You can get the final balanced equation in seconds. Clear? So this is about the oxidation number method. Now, to the extent possible, we'll try whatever knowledge we have gained so far to solve questions. Clear, shall we? Now, this is the first question that we are solving here. Number of moles of H plus ions required by 1 mole of MnO4 minus to oxidize oxalate ion to CO2. Oxalate is what? C2O4 2 minus. That is going to turn into what? CO2. And then one more thing to note here is that when permanganate is oxidizing an oxalate to carbon dioxide, it is undergoing reduction. It undergoes reduction to Mn2 plus. This is an acidic medium because we have already started with finding out number of H plus ions. So when H plus ions are there, it means that it is an acidic medium. Now, if it does in a neutral medium, you get MnO2. If you do it in an alkaline medium, you get MnO4 minus, but MnO4 minus is not stable. So that will turn back into MnO2. So MnO2 is a common species that comes out of this permanganate in a neutral medium or in an alkaline medium. But in an acidic medium, you get Mn2 plus. So MnO4 minus can be active in all the three media. Whereas dichromate, if you are looking at, dichromate will function as an oxidizing agent only in an acidic medium. Is that clear? So here C2O4 2 minus turning into CO2, MnO4 minus turning into Mn2 plus. We need to balance this reaction first, right? So shall we use the oxidation number method? For this, it is +7. This is +2. The change is how much? The change is 5. Keep this in mind. Look at this oxidates carbon. This is +3. If you can do it and see, 2x minus 8 is equal to -2. So x is equal to +3. And here it is +4. So how much is the change? You might be tempted to putting this as 1, but then remind yourself that there are two carbons here which have to go from +3 to +4. So I'll write here 2 into +3, 2 into +4. So this is 2 into 1. So this is equal to 2 now. This is where a student can go wrong sometimes, out of, even if sufficient practice has been done, if the student has not taken sufficient care, right, he or she might end up putting this as 1 and the entire thing is messed up. So you'll have to be extra careful there. So how many atoms are going from this +3 state to +4 state? Look at only the reactants. Don't look at the products. You may have 4 carbons in the product. Never mind. Look at only the number of carbons on the reactant side. Keep that in mind. So this 2 is going to become the coefficient of MnO4 minus. So 2 MnO4 minus. And this 5 will become the coefficient of C2O4. So 5 C2O4 2 minus. Giving rise to what? CO2 and Mn2 plus, which we need to know because it is an acidic medium. MnO4 minus changes into Mn2 plus. Now look at the reactant coefficients and then adjust the coefficients of the product. How many carbons are there? There are 10 carbons, so put 10 CO2. So 5 into 2 is not. This 5 into this 2 is 10. And there are 2 Mn, so put 2. Now atoms other than oxygen and hydrogen are balanced. Now look at oxygen. How many oxygens are there on the left hand side? 2 into 4 is 8. 8 plus 4 is 8 plus 20 is 28. And this side only 20 is there. So I'll put 8 H2O. Is that clear? Look at this. So this 2 into this 4 is 8. And this 5 into this 4 is 20. So 20 plus 8 is 28. And this is only 20. So I put 8 H2O. By putting 8 H2O, I brought 16 hydrogens. I'll simply put this as 16 H plus. And this is an acidic medium, so I can leave it like that. Now for the question. How many moles of MnO4 minus are there? There are 2 moles. For every 2 moles, you require how many H plus? You require 16 H plus. But you are being asked for only 1 mole. So it should be by 2. If that is by 2, this is also by 2. So answer is what? 8. Clear? I hope this is clear. We have balanced this reaction by the oxidation number method. You can also try it with the ion electron method. I think one of the questions here will ask you to do through the ion electron method. So they will employ the ion electron method. But because here oxidation number method is the quickest and we are falling short of time, so we'll use the oxidation number method wherever required, wherever possible, right? And then we'll move on to the place where ion electron method is specifically asked. There we'll do it. Clear? Now here, if the above equation is balanced with integer coefficient. So first of all, let us look at this MnO4 minus. We are doing what method? Oxidation number method. And then I minus is turning into I2. Now this is +7. You can do it and then find out this is +4. And the change is 3, right? There is only 1 Mn. So look at 3 as 3 only, not 3 into something. Now iodide is -1 because that is a charge. And iodine is 0. And there is only 1 iodine on the left hand side. So leave it like that. So this is 1. So this 1 will become the coefficient of MnO4 minus. And the 3 will become the coefficient of I minus. Gives rise to what? I2 plus MnO2. Don't look at the OH minus. That is only a medium part. Don't look at the water. That will come automatically. Now there are how many Mns? There is 1 Mn. So leave it like that. How many iodines are there? The 3 iodines. So I'll put 3 by 2 here. And then how many oxygens have come? This is 4 oxygens, that is 2 oxygens. So I'll put 2 H2O. Here. And then for 2 H2O, how many H plus have come? Oxygens have balanced, got balanced. 4 oxygens, 2 oxygens here. So 2 oxygens there. But then hydrogens have come. There are 4 hydrogens. So I'll put here 4H plus. But is H plus allowed? H plus is not allowed. It is in basic medium. It is OH minus. So I'll have to add equal number of OH minus on both the sides. Here, this is the technique that you have to employ for a basic medium or an alkaline medium. So do it as if it is an acidic medium. So you put the H plus and then remind yourself that this is in a basic medium. So in a basic medium, H plus is not allowed. To remove H plus, what do we need? We need equal number of OH minus ions. Where when I add 4 OH minus on the left hand side, I also need to add it on the right hand side, because otherwise the reaction will be thrown out of balance. So when we do this, the very purpose of doing this is to make this H plus turn into H2O. So we got 4 H2O. So I'll pick the H2O from there, and then minus 2 H2O will make this 2 H2O. Here. So this I'll remove. So I'll put this here. The summary of this I'm going to put it here. MnO4 minus plus 3I minus plus 2H2O gives rise to 3 by 2 I2 plus MnO2 plus 4 OH minus. But then he said integer coefficients. The coefficients need to be integer. So I'll need to remove this half in the bottom. So I'll have to multiply this with 2. So this will become 2 MnO4 minus. That will become 6 iodides. This will become 4 H2O. This will become 3 I2. That will become 2 MnO2, and that will become 8 OH minus. So we need to find out the value of this Z, which is equal to 8. I hope this is clear. So first we got 3 by 2, but then 3 by 2 is not allowed because we need integer coefficients. So 3 by 2 cannot be used. So I multiplied the entire thing with 2. So we got 8 OH minus. So Z is equal to 8. I hope this is clear. So we have used a basic medium, but still we have used oxidation number method because that is the quickest. I hope this is clear. So otherwise you can spend some time on this once again and then go through to make things clear. Shall we move on to the next question? Now in this, there is acid medium. There is acidic medium here. H plus is being there. So again, oxidation number method, Cr2O7 2 minus turning into Cr3 plus. Then Fe2 plus turning into Fe3 plus. That is all we need to look at. Water and H plus, they are part of the medium. So don't worry about them. Dichromate's chromium will have plus 6. And here it is simply plus 3 because there is a charge. Shall we blindly put 3? No, there are 2 chromiums. So 2 into plus 6 gives rise to 2 into plus 6. So this is 2 into 3, which is 6. Clear? And here it is simply 1. That 1 will become the coefficient of Cr2O7 2 minus, and the 6 will become the coefficient of Fe2 plus. And this whole thing is equal to what? Cr3 plus Fe3 plus. Look at the left hand side and balance the right hand side. There are 2 chromiums, so put 2 Cr3 plus. There are 6 Fe2 plus, so put 6 Fe3 plus. Now look at the oxygens. There are 7 oxygens on the left hand side. There is no oxygen on the right hand side. So put 7 H2O. And then while putting 7 H2O, we brought in 14 hydrogens. So put 14 H plus. Right? Now at the end of this balancing, always check whether the charges are also balanced. Now this is 14 plus and 12 plus is 26. 26 minus 2 is 24. On the right hand side, 6 plus 18 is also 24. Balanced. That's it. Now look at what is being asked. X plus Y plus Z. X is what? 14. Y is what? Y is for Cr. So 2. Z is what for H2O? 7. So 14 plus 2, 16 plus 7 is 23. So answer is 23. I hope this is clear. So this is again use of oxidation number method, but then the medium is acidic medium. But then a different question where the coefficients are to be added up and then found out. This is Fe. This E is not a subscript. It is along the line, is it not? This is Fe. and this is also the Fe there. It's not a subscript. Clear? Shall we move on to the next question now? Right? In alkaline medium, I think this is the simplest question in all the cases that we have seen so far. Permanganate ion, MnO4 minus, in an alkaline medium is going to turn into what? Is going to turn into MnO2, we said. Is it not? This is +7. This is +4. For 7 to become 4, we need to do -3. -3 means what? Adding 3 electrons. So gain of electrons is 3. Clear? So this is the simplest one that we have seen so far. So this is one very important thing. We said permanganate actually turns into manganate, but manganate is not stable. It will convert into MnO2. So overall, there is a +7 turning into a +4. Otherwise, it would have passed through an MnO4 2 minus, which is +6. So the gain would be only 1 electron, is it not? But this is not the end. The end is this. So from 7, we have to go up to 4, not stop at 6. So it is 3. I hope this is clear. Now the sum of oxidation state of metals in this Fe, pentacarbonyl, iron pentacarbonyl, BO2 plus, and then WO3 is. Now this carbonyl, Fe, CO taken 4 times, so taken 5 times, iron pentacarbonyl, most of the carbonyls are having 0 oxidation state for the metal. So that is 0. Now we'll do it for VO2 plus. 2 plus is on top. So V is X, oxygen is -2, and that whole thing is equal to +2. So X is equal to +4. And then WO3, tungsten. So X plus 3 into -2 is equal to 0. So X is +6. A +6 here, a +4 there, and a 0 there. Add up, it should be simply 10. The 4 and the 6 and the 0. Clear? Next question. I think this is also the simplest, one of the simplest ones. Now in ammonium phosphomolybdate, the oxidation state of MO is. Now we need to know what is the formula for this ammonium phosphomolybdate. You know that this is NH4 taken 3 times, PO4, 12 MoO3, which can be put like this now. NH4 taken 3 times P. So this is translate to that. Now ammonium is +1. So 3 into +1, and phosphate is -3. Those things will cancel out. So if I remove this, look at this now. So this +3 and that -3 cancels out. So this entire thing is neutral now. So MoO3 is like that WO3, is it not? So X plus 3 into -2 is equal to 0. So X is +6. So answer is +6. Clear? Ammonium phosphomolybdate has got what as the color? It is yellow color. This is used in the estimation of phosphorus, isn't it? Sum of oxidation states of bromine and bromic acid and perbromic acid. Now this is hypobromous acid. This is bromous acid. This is bromic acid. This is perbromic acid. Now, if you're looking at these two, bromic and perbromic, so you can take this HO as -1. So -1 plus X plus 2 into -2 is equal to 0. So X is what? X is +3. Correct? Look at the next one. -1 plus X plus 3 into -2 is equal to 0. So this is +5. Bromic acid, perbromic acid. Add up. Bromic is what? Bromic is, have we made any mistake here? +1 -2, HOBr. There is some mistake done. This is +1. This is +3. I'm sorry. This is +5 and this is +7. Correct. Now, if you look at the simple thing, HBr O3, HBr O4. So plus 1 plus x plus 3 into minus 2 is equal to 0. So where we have made the mistake. So this is plus 5. Yes, this is plus 5. And then plus 1 plus x plus 4 into minus 2 is equal to 0. So x is plus 7. Together it will be plus 12. Clear? So sum of oxidation states. So somewhere we have made a mistake there. Check that part. This part is clear for us. This is HBrO3, which is actually in the form of HOBrO2. Clear? Next, oxidation rate of phosphorus in hypophosphoric acid. Structure: HO, P double bond O, OH, P double bond O, OH, and then an OH. So this is hypophosphoric acid. Now you can put this as H4P2O6, is it? 1, 2, 3, 4, 5, and then 6. Yes. So 4 into plus 1 plus 2x plus 6 into minus 2, that whole thing is equal to 0. So x is plus 4. Clear? If it was pyrophosphoric acid, one oxygen will be there in between, and then it will be plus 6. Clear? Dichromate ion is treated with base, and what will be the oxidation number of chromium in the product formed? Dichromate ion is Cr2O7 2 minus. When you add base, it will turn into CrO4 2 minus. This is yellow in color and that is orange. In fact, this reaction is reversible. So when you add OH minus, it will turn into that. When you add H plus, that will turn back into this. So orange to yellow, yellow to orange can happen, right, with a change in pH. Now look at this reaction. Cr2O7 2 minus plus 2OH minus gives rise to 2CrO4 2 minus plus H2. This is a reaction, right? So CrO4 2 minus is what? X plus 4 into minus 2 is equal to minus 2. So this is plus 6. It was also plus 6 here. So when dichromate changes into chromate, there is no change in oxidation number. It's not a redox reaction. Clear? So the answer is plus 6. The oxidation states of transition metal atoms in these things are X, Y, and Z. So for the first one, you know it is plus 6. For the second one, you know it is plus 7. The third one, you're going to do the calculation here. Potassium is always plus 1 because it is group 1 element, plus iron X plus 4 into minus 2 equals 0. So X is how much? X is plus 6. So this is plus 6. So 13 plus 6, 19. Clear? Next question. Now this is somewhat involved one. Now K2Cr2O7 is going to interact with ferrous oxalate. Ferrous oxalate means FeC2O4. The ferrous is also oxidized. The oxalate is also oxidized. Now the change in oxidation number for this, you know that this is plus electron. If I can balance this, this is ion electron method that we are employing. This will be 2 electrons. So there are 3 electrons involved in this. And then in dichromate, Cr2O7 2 minus turning into Cr3 plus. This is plus 6 and that is plus 3. There are 2 such chromiums. So 2 chromiums to 2 chromiums will be 6 here. So for every 6 electrons, 6 moles of electrons. So here the change in oxidation number is how much? 6. For their change in oxidation number is 3 for them. So now, shall we say that the balancing shows that it is 3 dichromate equivalent to 6 FeC2O4? Because this 6 will become the coefficient of FeC2O4 and the 3 will become the coefficient of Cr2O7 2 minus. Or shall we say that number of moles of Cr2O7 2 minus is half the number of moles of FeC2O4? Correct? Now, how do you get the number of moles of dichromate? Molarity into volume. That I'm going to put it here. Molarity is how much? 0.02 into volume. Volume, you should take it in liters, is equal to, that is, this is the number of moles of dichromate, half the number of moles of ferrous oxalate. Ferrous oxalate means 0.288 divided by Fe 56, 2 carbons 24, 4 oxygen 64, add up 6 plus 4, 10 plus 4, and this is 144. Clear? So from this we need to solve the V, value of V. This is anyhow going 2 times. So this will become how much? 2 and 2 will cancel out. So this is 1. So 2 into 50 is 1. So it is 50 ml. Clear? So we've employed here the ion electron method to get the N factor. N factor is the change in oxidation number. Here also the change in oxidation number we have found out. And then we have got this volume as, actually you'll get this as, this is in liters, is it not? But we want it in ml because it is given here already that we need the answer in ml. Clear? Next, which of the following reactions are disproportionation? We know that this is +1 coming down to 0 and going up to +2, disproportionation. This is +6 going up to +7 coming down to +4, disproportionation. Whereas here this is +7 coming down to +6 and also coming down to +4. This is not disproportionation. It should go up and it should come down. That is what is disproportionation. So C is not disproportionation. And then what is D? D is comproportionation. This is +7, this is +2, and they're together going to become +4. Clear? If I might change the pen here. Yeah. This is how much? This is +7. This is +2. And together they're going to turn into +4. So for 2 there is a rise, but for 7 there is a fall. So this is a comproportionation reaction. Clear? So only A and B are disproportionation reactions. C is neither disproportionation nor comproportion, but it is a redox reaction. So A and B only, option B it is. Clear? Next, order of N compounds in its decreasing oxidation states. So HNO3 is +5, NO +2, N2 0, NH4Cl is -3. So I think it is in that order. Yes, A it is. Clear? Now this is a redox reaction. Identify the species which is oxidized and the one which is reduced. Now look at this. Copper is in +1 oxidation state. Also here, but here it is 0 because it is element. Sulfur is in -2 oxidation state. But the same sulfur here is in +4 oxidation state. So sulfide is undergoing oxidation. So strictly speaking, sulfide is a reducing agent or reductant, which undergoes oxidation. A reducing agent undergoes oxidation. It reduces copper in the +1 state to copper in the 0 state. So cuprous is the oxidant here because it is undergoing reduction from +1 to 0. Clear? So we have mentioned what is the oxidant and what is the reductant and what is undergoing oxidation. Sulfide is undergoing oxidation, therefore it is a reductant. Cuprous is undergoing reduction, therefore it is the oxidant here. Clear? Can we store copper sulfate in gold vessel? Copper sulfate will contain what? Cu2 plus gold if you are writing. And here there is auric ion given here. I'll put auric here and then copper. If this combination is not changing into this, then it can be stored. Otherwise, if there is a chemical reaction, what is going to happen? The gold vessel is going to turn into gold ions. Means there is a dissolving of the vessel itself. So let us look at whether this is possible or not. Now, copper 2+ to copper is what? Reduction from +2 to 0. And this is oxidation. We know that reduction happens at cathode and oxidation happens at anode. So what is E cell? E cell is E of copper, sorry, E of cathode minus E of anode. E of copper, copper is how much? 0.34 minus E of gold, which is 1.5. This is negative. So when E cell is negative, the reaction will not happen. So this reaction is not happening. So gold is safe. So we can store, right? We can store copper sulfate in a gold vessel. Clear? Nothing will happen. I think this I can leave it to you. Should be simpler enough. This will do now. Ion electron method. Zinc to zinc 2+ and NO3- to NH4+ it is. So I'll simply add 2 electrons here. This part is done. For the other part, I'll have to balance the oxygen. So I'll put 3H2O. How many hydrogens did I get? 6 + 4 is 10. So I'll put 10H+ here. So nitrogen is balanced, oxygens are balanced, hydrogen is also balanced. Now this is 1+ and that is 10+. So I'll add 9 electrons here. Clear? Check once again. This is NO3- turning into NH4+. NO3- has got 1 nitrogen, so it is balanced already. Oxygens are 3, so I put 3H2O. Because I brought 3H2O, there are 6 + 4, 10 hydrogens. So 10H+ I have put. And that side is 1+. This side is NO3- and 10H+ is 9. Is it not? So I'll put 8 electrons. 8 it is it not? So 10 - 1 is 9. 9 - 8 is 1. So that is balanced. This I'll have to multiply with 4 because number of electrons need to be equated. So I'll put 4 zinc gives rise to 4 Zn2+ plus 8 electrons. And this is as it is. So left plus left is equal to right plus right. So I'll add the left plus left here. 4 Zn plus NO3- plus 10H+ plus 8 electrons gives rise to 4 Zn2+ plus 8 electrons plus NH4+ plus 3H2O. We can cancel out the 8 electrons because we need to remove the electrons at the end. Now check for the balance of mass as well as charge. 4 Zn, yes, equal. 1 N, yes. 10 hydrogens. 6 + 4 is 10, correct. Now look for the charges. So 10 - 1 is 9. 8 + 1, 8 + 1 is also 9. So this is balanced. This is an acidic medium, so I have left the H+ as it is. Clear? So this is how we balance reactions, redox reactions. We have used oxidation number method as well as ion electron method. I hope this session was sufficiently useful for you, right? Though it was something of a hurrying type because we had to take up things as many as possible in a single session. So we had to do that hurry. A little rushing was there, but then I hope all the things that we have covered here, are sufficiently understandable. And with this, we'll conclude this session once again with the details of our YouTube channel and then other related things. So I hope this session was sufficiently useful. You go through all these things once again and subscribe to this channel. You'll get interesting videos, and then see to it that you make time as your partner for your successful journey to get through various entrance exams, cracking all the exams, and then getting into good colleges. Thank you. Best wishes.